Let's generalize the dot product notion to matrices. You can see this overly used matrix once again. 5, 12, 6, minus 3, 0, 14. If I want to multiply it by 3, we would have a scalar times a matrix situation. Similar to what we saw in the last lesson, the shape of the matrix doesn't change, it just gets scaled. We keep the shape and multiply each element by 3. The result is 15, 36, 18, minus 9, 0, 42. All right, that's easy. But how do we multiply a matrix with another matrix? Using the same concept, the dot product, we can multiply two matrices. There is a compatibility measure here too. We can only multiply a matrix of dimensions m by n with a matrix of dimensions n by k. Basically, the second dimension of the first matrix has to match the first dimension of the second matrix. So, we can multiply a 2 by 3 matrix with a 3 by 1 matrix. Actually, we can multiply it by a 3 by 2, 3 by 3, 3 by 4, and so on until 3 by k matrix. What's important is that those 3's are matching. Similarly, if I want to multiply a 5 by 7 matrix, compatible matrices for multiplication are 7 by 1, 7 by 2, 7 by 7, and so on. Okay, fair. What about the dimensions of the product itself? When multiplying an m by n matrix with an n by k matrix, the output is an m by k matrix. For instance, a 2 by 3 matrix times a 3 by 6 matrix will give us a 2 by 6 matrix. A 3 by 4 matrix times a 4 by 2 matrix will give us a 3 by 2 matrix. A 100 by 300 matrix times 300 by 3 matrix will result in a 100 by 3 matrix. Basically, whichever dimension is repeating will disappear in the resulting matrix. Okay, now we know the compatibility measure. How do we actually multiply matrices then? Let's start with two matrices, 2, 8, minus 4, and 1, minus 7, 3. Actually, these are two vectors, or 3 by 1 matrices, right? In order to multiply them, they need to have matching forms. To find their dot product, we transpose the first one and get a 1 by 3 times a 3 by 1 form. This is done because when we have a dot product, we always multiply a row vector times a column vector. Remember that. The result of this multiplication is a 1 by 1 form, or a scalar. We reach this scalar by multiplying the corresponding elements and summing everything up. We've already talked about that, we just didn't know the concept was the same. All right. Time to take the two matrices and multiply them. The first is the same one from the beginning of the example. The second will be a 3 by 2 matrix. 2 minus 1, 8, 0, 3, 0. The first thing we need to do is check their compatibility. 2 by 3 times 3 by 2. The forms are matching, so we are good to go. The next step is to find the shape of the output matrix. The matching dimension disappears, so the resulting shape is 2 by 2. Finally, we must do that multiplication itself. Let me remind you two important things. First, matrices are nothing more than a collection of vectors. And second, when we have a dot product, we always multiply a row vector times a column vector. How does this apply to our case? Well, the first matrix is made up of two row vectors, 5, 12, 6, and minus 3, 0, 14. The second matrix is made up of two column vectors, 2, 8, 3, and minus 1, 0, 0. In order to find the dot product of the two matrices, we just need to find the dot product of the vectors they are made of. Let's find the dot product of 5, 12, 6, and 2, 8, 3. It is 5 times 2 plus 12 times 8 plus 6 times 3, which equals 124. Easy. 124 is also the first element of the output matrix. Next, we find the dot product of 5, 12, 6 with the second vector, -1, 0, 0. It is 5 times -1 plus 12 times 0 plus 6 times 0. The result is -5, which is the second element of the output matrix. Great! Let's get to the second row of the initial matrix. There we have -3, 0, 14. We repeat the same procedure. The dot product of the vector -3, 0, 14 and 2a3 equals -3 times 2 plus 0 times 8 plus 14 times 3. We get 36. This is the first value on the second row of the output matrix. Notice that the row vectors from the first matrix determine the row in the output matrix. In the same way, the column vectors from the second matrix determine the column of the respective value. Finally, we find the last dot product. We get 3, and the product matrix has been found. Great! In terms of code, things are very simple. We use the method np dot and the two matrices and immediately get the result. All right! While this lesson is getting a bit long, we should do another example just to solidify the knowledge. I'll take two big matrices, this one and that one. The first matrix is 4 by 5. The second matrix is 5 by 2. First things first, are the matrices compatible? Yes, they are. Second, what will the shape of the output matrix be? Of course, 4 by 2. Next, let's divide the first matrix into row vectors and the second matrix into column vectors. There is a total of 4 row vectors and 2 column vectors. In order to start multiplying, we must find the dot product of the first row vector and the first column vector. The result we get is -71. Next, we multiply the first row vector with the second column vector. We get -48. We continue in the known way until we fill the product matrix. All right, linear algebra doesn't seem that hard after all. Do you feel comfortable? Let's do one more. This matrix multiplied by that one. A 3 by 4 matrix times a 2 by 3 matrix. What will the dimensions of the output matrix be? 3 by 3, no? Wait. It's not 3 by 3. In fact, it's nothing. The two matrices are not compatible. It is very important to remember that more often than not, you will not be able to multiply two matrices. So, please take good note of the shapes. Thanks for watching.